Hello, good morning. Let's start with another concept that is disjoint set union. So this is the concept used in graphs. So this is the data structure used in the graph. So let's start with it. So for this we need some prerequisites. That is, you need to know basic programming. Apart from this, you need some basic idea on trees. What are nodes? What are edges? How we are going to represent uh, in codes. Secondly, after this, we need some algorithm ideas. In algorithm, basically, we need some idea on recursive algorithm, how recursive trees form, how we form stack, and that's it. After this, let's see idea of what DSU is going to provide us. So DSU is going to provide us that we want to combine two trees. We are given two trees and we want to combine two trees. Apart from this, we need a checker to check whether two nodes belong to same tree or not. So after this, what we are going to mean by combining two trees? Let's take example. Suppose we are given a tree with node 1, 2 and 3, and we are given another tree with node 4 and 5. So what we want to do is want to combine these two trees. So what want to do is that initially we want just represent this two tree in the form of parent array. So for one parent is going to be itself, for two parent is one, for three parent is one, and for four parent itself, for five parent is four. This is the representation of the graph of tree which we are given. So next we want to merge the node 1 and 4. So merging, we just going to create an edge between 1 and 4 there, and this is going to merge these two tree. Now the problem is that who is going to be its parent? Now as of now made fourth parent as 1. So now updated parent array become that fourth parent become 1. So this is the combined operation of two trees. Now next need what we mean by checking whether two nodes belong to same tree or not. Let's take example. Suppose you want to check whether 2 and 3 belong to same tree or not. As we can see where both 2 and 3 belong to same tree, and if we start traveling from 2 and 3 across its parent, then we are definitely going to meet at a node. And what about 2 and 5? As 2 and 3, 5 belong to different tree, and if we start keep on traveling to its parent, then we definitely not going to meet at same node, as 2 is going to reach at 1 and 5 is going to reach at 4, as both from 1 and 4 we cannot move across these nodes. So definitely these not belonging to same tree. Okay. So these are two ideas, that combining two trees and checking whether two nodes belonging to not. These are the functionality provided by DSU data structure. So next start, we want to do these operation less time as possible. So we want to do these operation in most optimized way. Okay. Okay. Let's start with the solution. So let's start with the brute force idea. Whatever we are able to do is then we will try to optimize it. Okay, find most simple way to solve this problem. Okay, now let's how we are going to represent the tree. So what we want to do is that we represent the tree in such a specific format, so we can just do this operation in most optimized way. As of now, let's represent this tree in the form of parent array. As you can already see how we are representing these trees. Let's represent two trees in one array instead of two. So if we are given two trees, we do not want to create two separate array and store them in different array. And so what we want to do is that if we are given a tree with node 1 to n and a tree with 1 to m, so we just going to represent these two in one single array of size n plus m. So first tree will line in the array index from 1 to n, and from second tree will line in node from n plus 1 to n plus m. So total size of nodes will be sum of the nodes in two tree. So if we are going to form some initial tree, then keep on merging nodes. So if we are given some initial tree, and we want to form some edge between those two nodes, we going to use the combine function of the DSU. That is combine function. What we are going to combine two trees. So if we want, we are given initially we form some edges between tree, and we want to just create a end. We just going to combine those two nodes. Combined two nodes will definitely going to merge those trees. we are going to find. Okay. So, okay. So now what method we are going to need it? So first of all, we need a constructor. So constructor, we just going to create this initial parent array. This constructor going to initialize this parent array each node. So as of now, when we are going to initialize this parent array, initially what we want that each node point to itself. So initially each node is lying individually and its parent is going to be itself. Okay. Secondly, we need a find method. What find method is going to do is that for a given node, it's going to find its root node. Okay. Suppose we are given node A, and for node A, what to the tree which node is belonging, we want to find its root node. Next, we need a merge function. In merge function, what we are doing that we are giving two node as input, and we want to merge the tree to which these two nodes are belonging. Suppose we are given node A and node B, want to merge tree having node A and node B. Okay. But if a node and B are belonging to same tree, that definitely we not want to merge the tree, and there's no need of it. Okay. So suppose now we want to move towards the code. Okay, let's see the code. So first we need an initial parent array of size n plus 1. As of now, I want to construct array of index 1. So for each node, its parent is going to be itself. Next, we need a find method. Find method, what is going to do is that in first line, we are checking whether its parent, it itself, if we have reached to the root node, then it definitely going to be its parent to itself. So we are just going to return the this root node. If this is not the case, we just want to find the root node of its parent. Hmm. Okay, now let's take example to understand it. Suppose if we want to the find of I, that is as 5 is not parent of itself, so this is definitely not going to be root node. So what want to do is that find the root node of its parent, that is 3. Now 3, for 3, as this is not node, as this is not parent of itself, we want to find root node of its parent of I, that is 1. Now as for 1, it is parent of itself, then definitely this is going to be the root node. So this is now we going to just return this 1 to 3, and from 3 we just going to return to 5, and this for 5 not definitely now the root node going to be the 1. Okay. Next, we need a merge function. So merge function, as we know that it is going to merge the two trees having node I and j. So let's see the code. For given two node I and j, for I we want to find its root node and update I. That is for I, the node belonging to the tree, we find its root and update I. Similarly for j, find its tree's node and update it. If both root node are same, then definitely not we need to merge it. As let's take example, if both the node going to belong to same tree, then definitely its root node going to be point to same node, as these two trees are in same tree. If these are in same tree, then root node, as there is only one root node in a tree, so definitely there's going to point to same node. So if they are same, then there's no need to merge them. If this is not the case, what we want to do is for I make its parent to j. So now I not going to point to j. So we going to create a edge from I to j. So now both the trees are going to merge, and finally root node going to be j. So now let's example. Suppose we want to merge 2 and 5. So for 2 going to find its root node, that is 1, and for 5 we are going to find its root node. So now we have two node 1 and 4 that we want to merge. So now we want to merge these parent node, that is 1 and 4. So okay, let's okay, now we want to merge these two nodes, that is 1 and 4. So for that I is pointing to 1 and j is pointing to 4. So we want to merge this. For parent of I, now we just going to point to j. So parent of I that is 1, now going to point to j. So we are going to update this for 1, now parent is 1. So this is the merge function, we are merging these two tree. So now let's, now finally the node, root node going to be the 4. So we are returning this final root node, that is 4. So what, this method is going to be too slow. Why? Let's see. Suppose we are giving some node as 1 2 3 4, and we merged 1 and 2 and just point 1 to 2. Similarly, we merged 2 and 3 and point 2 to 3, and similarly we merged 3 and 4 and point 3 to 4. Then this is going to form a long chain. And if we are going to find somehow find parent of 1, then we need to travel this chain. So for 1 we move to till last node in a chain. So this is going to take O of n time, as this is going to be too slow. So this is the chain, and we just keep on merging, then this is going to form this chain. And if we want to find parent of 5, then we need to travel across this chain. And if there are multiple queries, then each time we need to travel to all its nodes, and this is definitely going to be too slow. So is we have wasted time at discussing this slow solution? Not so really. So definitely we need, just definitely we need some optimization in the solution. So we just need two optimization. And with these two optimization, this O of n solution is going to be convert to O of 1. So let's see. If you want, you can pause this video and think what optimization we need. So we need just 2-3 line of code changes in the existing solution we discussed so far. So let's move. So these two optimization are, one is path compression, and that is union by size. So in path compression, we want to update the find method. So find method, the first line going to remain it is, and if in second line, when we are going to find the root node its parent, so we just going to store it and update the parent of current node. So suppose we are finding parent of node some x, and we are moving upward. So whenever we will reach node, we going to return that root node, and all the node which we going to lie from x to across the root node, we are just going to update its parent. And what parent is going to update is, now this all these node directly going to point to its root node. So all the node now, all the edges going to remove from x to root node, and directly these edges going to point to root node. Let's take example. Suppose we want to find the root node of 5. So first line, as this is not the root node, call the second line, that is find parent root node of its parent, that is 3. So we want to find root node of 3, as 3 is not settling first line, that is it's not a root node. We want to find root node of its parent, that is 1, as 1 is root node, as it is satisfying first line, so it's going to return this 1. So when we are moving back to the recursion, we update the p value. So p will be returned value, that is 1. And for 3, we are going to update its parent to its 1, as it's already 1, that is it's already pointing to root node there. We no need to update this. So, and return this 1, as this is the now new parent, root parent of 3. So when we are coming back from 3 to 5, we return it value going to 1. We are going to store p as 1 and update 5 parent to 1. That is, now this is edge is going to be root, that is 5 is not now going to point to 3, and for 5 now updated with 1. So this new node, new edge is added, that is 5 is pointing to now 1. Suppose there are many nodes across this chain when we are moving deeper in the stack, so all the node not the edges in this stack is going to remove, and not directly this all these node going to point to root node, that is 1. So this is decreasing the depth of the tree. So this is the first optimization. Let's see the second, that is union by size. So here we need to update the merge function. So these two lines are same. If the second line is also same, say now we are just storing the size of each tree. So if within each root node, we are going to store the size of the tree to which this root node is present. So So this is the concept of merging smaller to large. So I am going to cover this concept in another video. So we will cover in that part. So I just going to do rough ideas. So for I and j, checking whether which is the bigger size tree, as we have already updated I and j to its root node. So this size array is storing the size of the current uh, tree root. Okay. Now, as we checking whether size I and j, if I is a smaller size than j, we are going to swap that. So at last, I is the t- tree of root node of tree whose size is going to be bigger, and j is the root node of tree whose size is going to be smaller. So next line, what we want to do is that the j, now its parent going to point to I. So a node will be connected from j to I. That is a node from a smaller tree going to point to the root node of the tree of bigger size. So what want to do is that tree of smaller size going to merge with the tree of size bigger size. So its parent j's parent is going to be I, and now we need to update the size of. So now finally the root node is going to be I, as I is now a new root tree. Its size need to be updated as j's tree is merging with I. So j i's size need to be added with the size of j j. So j store the size of the second tree. So we just going to add the size to its I, and finally I is going to definitely going to be the final root node. So we just going to return this. So these are the two optimizations. There is path compression and union by size. So these compression convert the O of n time complexity to O of 1. So, and there is something known as inverse Ackermann function. This prove thus this time complexity O of n to O of 1. This I will cover in definitely in another video. As of now, I assume that this is converting O of n to O of 1 time complexity. So this is the final code. So we are in constructor, we creating two array, one parent array of size n plus 1 and size array of n plus 1. Indexing we are covering as from one in base indexing. Size of, as initially all node is of size 1, so we will initialize as 1, and parent each node now initially is pointing to itself, so its parent is going to be 1. Next we need find in first line we are checking whether this node is pointing to itself. If it is pointing, then this is definitely going to be root node. Next we are finding root node of its parent and store it. So move to parent node and find its root, and if we find it, just store it and update its current node's parent. So whatever node belonging, so we find the parent's root node, and for current node we just remove the age from current node to its parent and move its age to root node. So all the node lying from current node till root node, we just remove these edges, and all these is nodes going now pointing to root node. Okay, next we need merge function. In merge function we update each nodes to its root node. So for I we are finding its root node and update I, and for j we find its root node and update j. If both the root nodes are same, that is they are belonging to same tree, there is no need to merge them. If they are not, we need size compression, union by size. So we will check with the size of I and j trees. If size of j is smaller than size of j, then I is a tree with smaller size than j. We want to swap it. So at last we want to make j as large, I as larger and j as smaller. So at last what we want to do is merge smaller with bigger. So parent of j, that is smaller tree, now going to point to tree with of larger size, that is I. So parent of j become I, and finally the root node become I. So as both the trees are merged, we need to update the size of I, as now j is merged. So we need to add a j tree size to I tree i's, and finally I is going to be definitely the final root node. We need to return it. Think I hope this video is clear. If you have any suggestion, please ping in a comment. I will definitely going to reply it. Thank you. Have a good day. Bye.